So, introduction to gRPC by Michał Pawlik. But before that, let me say a couple of words about Michał. And by the way, I am the one who saw this presentation already. A very nice one, by the way. So, who is Michał? Michał is a site reliability engineer in Nokia GSCS network engineering. He's a software developer professionally, like for 7 years already, author of publications for Programista magazine, an advocate of Scala programming language and functional programming, Linux user, which is pretty natural in, let's say, this background, Bachelor of Computer Science at the Wrocław University of Technology. In his free time, he solves puzzles of escape rooms and plays board games amongst the others. So once again, please clap your hands for our next presenter, Michał Pawlik, please. Thank you.
Thank you.
Introduction to gRPC.
Thank you. Thank you for this introduction. So, as you said, we are going to talk about gRPC today, which is going to be something about communicating services in cloud. So, gRPC, what is it? gRPC is, following the definition from their website, is high-performance, open-source, universal RPC framework. So, most of those words are likely understandable despite of this RPC. What might it mean? Well, RPC is inter-process communication technique used between clients and servers to communicate them. So some of you might recall that the RPC, well, in the good old Java times, it wasn't like quite cool technology. It had some problems, but RPC is an idea and it had some implementations. And gRPC, which is the thing we are going to talk about today, is quite a new approach, hopefully more understandable, more user-friendly. But beforehand, if we're talking about applications that talk to each other, clients and servers, there is something that might come to your mind quicker than RPCs, which is most popular these days, which is REST. How many of you know what is RESTful? Okay, like 80% of you, that's cool. So REST is as well an idea. So REST, representational state transfer, means that there is a server that has some kind of state, and there are clients that want to push some modifications to the state. They want to list the state from the server. And the implementation, most popular one these days, is JSON over HTTP1, which has its own advantages. We use it every day. It's easy to learn because you simply convert your objects to some sort of JSON, send it via client, HTTP client, which is probably available in any language. It's very simple to implement. It's common. I can't imagine any web service that's out there that doesn't use like REST in terms of like the most popular applications. The serialization format when it comes to debugging or understanding what's going on in the talk between server and client is very simple to read, so we can debug it easily. But this approach to client-server discussion, this communication, has its own drawbacks. So first thing that comes to my mind is no built-in documentation support. So when we think REST is just the description of how do you construct a query. So you build some kind of object, like JSON object, for example. You push it with put, with get methodologies, but it doesn't imply any impact on how you document the API you have been creating. So there are, of course, like third-party documentation tools like Swagger, OpenAPI. We'll elaborate on this in a second. It requires some boilerplate because whenever you create a service that's going to talk about using RESTful API, then you always have to wrap around like HTTP client and serialization libraries. So this doesn't come completely for free. Versioning is pretty bad. I bet many of you had those problems implementing those REST APIs when you misspelled the field name and there were like many problems, or you wanted to deprecate a field, but there were those old clients that required it to be available. So it's not like flexible in this manner. There is no type safety because JSON is JavaScript based, so dynamic language. You can, of course, write some kind of JSON schema, but this is additional overhead on your implementation. JSON is also not very CPU-friendly in terms of serialization. It is quite, its compression, its serialization is quite expensive. And in days of like fast laptops and huge servers somewhere during the cloud, it shouldn't be like problem. But what comes to my mind is you have a smartphone in your pocket, and the smartphone also has to communicate with the services somehow. And if there are some CPU-intensive computations like JSON, serialization, deserialization, it influences your battery life. So if we could potentially have like a way to serialize something for less CPU operations, the better. We don't have built-in pagination support, so whenever you have like huge amount of data, you want to download it, many records, then you either have to produce like very large output and then consume it, so it takes time, it takes transfer, but you can implement pagination on your own. So this is additional boilerplate you have to deal with. And last but not the least, there is no valid way of triggering actions in REST. So REST is not designed for something like that. Imagine you have to create an API for a printer. You want to expose it, so you are not going to use REST because simply REST doesn't predict that you want to be pushing some, like, do such operation and that's over. You are not modifying a state. So REST is not perfect for like this kind of use case. Elaborating on this API aspect, this is an example taken from OpenAPI, namely Swagger.io. So here on the left-hand side, you have some unreadable, huge YAML that describes something, a part of API. On the right-hand side, you can see the documentation that's come out of it. Of course, when you have this kind of definition, you also are able to automatically generate client code, server code, and the content of this YAML is not really important. The important fact is that all those 58 lines that are visible here only support those two routes. So you have to write much, much more than this to describe whole service. So it doesn't like something funny to do, something like I would like to do. There is huge overhead to make sure that all the clients use the API as you would intend them to. So there is automated way of producing clients out of the documentation, and there are ways to document your APIs, but if they are convenient, if they are flexible to use, it's up to you to decide. Okay, so we talked about something we know already. So this JSON over HTTP, so-called REST. Let's finally talk about gRPC. Is it an alternative to REST? This is not something I'm going to prove today. This is a question you'll have to answer on your own. So, handful of facts before. gRPC, what does it mean? This is like recursive acronym, as in Linux. Meaning of the word Linux is not Unix. So with gRPC, gRPC is gRPC remote procedure calls. So that's all. Nothing really impressive. What's the background? This is a framework developed on open source since 2015. Beforehand, it was developed at Google internally, and this is direct successor of their internal RPC platform called Stubby. This brings us to main ideas. So Google, those guys quite know how to do business and do technology, so we can somehow trust them that they did invest enough to have this design well. This is a successor to Stubby. That means there was already a solution. They have learned on their problems with their internal solution, and hopefully gRPC solves things better. This is a project of CNCF, so this is it's not something that's going to die quickly. It's adapted in production by many big players, and the fact that's important for later, it uses protocol buffers for serialization. So no JSON inside. You could potentially exchange protocol buffers for JSON, but nobody uses JSON in production, according to my knowledge. What is protocol buffer? We'll explain in a second. Okay, what are the principles of gRPC? So this gRPC is based on services and messages. So something similar to when you start designing a service or architecture. You start with a blackboard to draw in boxes, then drawing arrows and saying, okay, this box sends messages like the user data to this one and so on. So basically in gRPC, you reflect that architecture in the descriptions of services and messages. gRPC is, of course, cross-platform, which means there are implementations of gRPC in many popular languages, most of popular languages. There is built-in streaming support. So going back to this example with pagination on APIs, you can simply stream data through gRPC. We'll cover that later. This is a layered solution that has a pluggable additional middlewares. So imagine you want to introduce some kind of authorization, authentication, then you simply put a middleware that's being executed before the message is received or sent, depending on if you're writing a client or a server. And one more thing, versioning support. So this is still something that was missing in JSON. You have versioning support because you use protocol buffers, and we, in a second, will explain how do you actually support versioning. The last fact is that it is layered. So at the moment, gRPC uses HTTP2 beneath the scenes. But because of the layered architecture, if there is a decision that HTTP is not sufficient or we have something more performant, for example, thanks to this architecture, you can simply exchange one networking layer to the other, and the end clients will not see any difference compared to REST JSON over HTTP, where you directly use the HTTP client. So, as I mentioned, there were other APCs in history. Compared to them, gRPC is asynchronous and non-blocking, so you don't have to wait for the messages. It also supports the streaming. It's very simple to define. So the format is not like huge XML or something likely to reflect the YAML shown you before, but it is very simple, and you'll see why in a second. It's message-based, so this is like you don't have mutable state during the connection or on the gRPC level. You, of course, can have mutable states in your service, but it's not implied by gRPC. It's open source, based on standards, which is not common in RPCs. It was not common when designing RPCs. There were also proprietary solutions. And this is how gRPC communication looks like. I don't want to dive too much into the details, but you can see server on the left-hand side, which is written in C++. Then you have two clients on the right-hand side, which is Ruby and Android Java client. I only wanted to show you the nomenclature that on the left-hand side you have a server, on the right-hand side you have the clients or so-called stubs. So further, if I'm gonna mention a stub, roughly it means just a client. And on the first view, this doesn't look like different from, for example, what you would draw when designing RESTful APIs. And last but not the least, in the terms of nomenclature, protobuf, which means protocol buffers. This is Google's idea for serializing data. Basically, protocol buffer defines a structure, so you can think of something like a class, and way to build a binary message out of it to the transportation layer. Okay, so we have some theory behind us. Let's try it out. So let's start with protocol buffers so that we can understand the language of gRPC. This is an totally random example of how you would write messages in protocol buffers in protobuf. So on the top, you can see there is some syntax definition. We'll code that later. There are some messages, two messages. You can think of a message schema, how every message should be structured when exchanging. So this is the thing you would normally express in YAML in OpenAPI or something. You can see that this is statically typed. There are type definitions on the left-hand side. You can see that there is an empty message. Why do we use empty messages? I will cover that in a second. What's the most strange one is that we have some kind of numbers on the right-hand side. This is unusual. Those guys are tag numbers. So in protobuffers, you use tag numbers because on the transportation layer, you don't exchange those names from the structure. So client might name the fields of message however they want, because on the transportation layer, there are only indexes. And this is the core of supporting the versioning, because if you want to deprecate a field, you simply stop sending the field and use another tag number for a new field. So there is a contract within gRPC between clients and servers that if a client wants to or expects a field number 2 or number 3, if it's not present, the client will assume that this field is 0 in its own type. So in case of a string, it's an empty string. In case of a number, it's 0, and so on. So this is the base of versioning support. We are not covering the details of version support because it would take another lecture, but this is how we approach the topic. So as I mentioned previously, you have messages and services in gRPC. So those are the messages, and on the bottom you can see how you define a service. So service also looks somehow similar to a class in any programming language. So you type a service and its name. Then you have RPCs. There are 4 mentions and they all differ. But you can think of RPC as a method that is being exposed by a service. And the simplest service you can define is based on exchanging single message for single message. So I want to request a data for a user of certain name or certain ID, and I receive the message, and that's all. Then you can define client-side streaming. Imagine you want to cover a use case where a user wants to upload a file for some kind of conversion or just leave it in database. Then a user might stream the data if it's huge, and when the stream is over, the server completes consuming the stream, it can send a single response. Then there is a client-side, there is a server-side streaming. Imagine you want to see our lecture here on YouTube, so you would simply send a request for the stream, and as long as the stream is online, you will receive messages in the stream. As soon as the stream is fully consumed, the contact is over. And last is bidirectional streaming. So you can imagine this is something like a phone call where 2 parties can exchange messages asynchronously during the lifetime of this both streams. And okay, so this is basically how the syntax looks like. Hopefully it's not too difficult, and hopefully it's similar enough to whatever language you prefer. So let's go through like real-life example. Let's define a shopping service. So the shop has like something like a product that it can offer to the client, and this is like very early stage. We only allow users to list products. So there is no like buying things, nothing this kind. So how would we approach this thing? So let's get started with protobuffer definition. This is something I want to focus on, that when using gRPC, you start by defining the interfaces. And this is quite fine approach because you are not bothered with the details of the technology you're going to be working with. You simply think in terms of a service that will provide some methods, some logic, and the messages that are being exchanged between the services that use them. So the definition, it starts with the syntax and the package, which are, in the first place, like less important. Syntax is simply proto3 because gRPC uses protocol buffers in this version. This is something you just leave and forget. Package is also for a programmer because whenever you generate files, we'll see how it happens in a second, but when you compile protobuffer, you receive a ready file in your programming language. So for example, in a second, we're going to compile this example to Go programming language, and we will receive some kind of Go language, and this implementations will land in package named gRPC introduction. So the product, think of a product like you can find in a online shopping site. So the product can have some sort of ID to make it unique, name, description, price, all those things have their own types specific to what they mean. Also to show you there are also complex types. So you can have lists, you can have maps to describe something more nested. You also can nest messages into messages. Then you have product list request, which is an empty message. How do you think, do we really need empty messages to be sent? Like, can you come up with any reason for that? Well, at the moment, empty request makes no sense, but there are two reasons to implement it. First of all, every RPC needs a message on the inside, on the input, and a message on the output. So this is to satisfy the syntax requirements, and also, like, the only thing we can say about any service that is being developed is that it's going to evolve, it's going to change. So in future, I can imagine that somebody that wants to list products will say, okay, but I only want products that start with the letter A or in the specific category or something. And especially if it's like mobile device that is being the one who requests, then you want to like take all the CPU intensive stuff on you. So the filters might come in future into this message. And basically that's all. We have designed our service and the messages it exchanges. So how do we approach the implementation? Let's start with Go. I'm going to skip that because this is just taken from the documentation. How do you install the compiler? What's important is that you use proto-C, point at the proto file, and receive Golang files in the output directory. Your only thing to do further is to import the produced package, and you can see that we alias it as a PB. Remember that because it was too little space to place the import in the second slide. So PB will be the thing we have generated out of the protobuffer. And the output, this is a piece of this output. We can see that the product that we have defined in our protobuffer, it's roughly a structure in Golang code created here. And similar files will be created for any programming language you will compile protobuf to. And how does our server look like? So going from the top, you can see that we have defined some kind of structure. How many of you are familiar with Golang? Okay, one like third at most. Okay, so for those of you who are not, in Golang, if you want to implement a interface, you are not doing it as explicitly, like for example in Java or somewhere else. We don't inherit or something. To make contract valid, to implement an interface, you simply create all the methods that are present in the interface. So you can see in the line number 7, there is a function called getProducts, which is named the same as the RPC we have declared. So basically, shop server is something that implements the business logic for the service we have declared. And going through the execution, first thing that happens is you open some sockets to be listening on. Then you create gRPC new server in the 19th line, which means gRPC server here is something that binds a port that's open to the business logic that we have created. We instantiate the shopping server. We create some 20 random products just to have something to serve, which means we create some internal like list of those products, and that's all. Then this is the important part. So we have this gRPC server. You can see that this is bound to this business logic. So in case you wanted to exchange those network layer, you would potentially simply change this gRPC server to something different. Sorry, you would change this list here as the listener to listen on some different network layer, whatever implementation would it be. And last but not the least, the implementation of our strict business logic. So we have request coming in, and there is a stream that we will put the data onto. And as long as we put the data, the client will consume them. And when the function returns nil, which means there is no error, the stream is getting closed by its own, and we're done talking. So basically, this is the implementation. So in every language, it would look similar. So you have to open some kind of socket, then you have to provide an implementation of the service and bind each other to, and that's all. Building client is much simpler because in gRPC you receive clients for free, as with most automatic documentation to code generators. Let's quickly go through it. So first of all, we dial to this socket that is being opened. Then we build a new client. Remember pb dot something. pb is the thing we have generated with protocol buffers. Then we create context, which in Golang means this is the common way of providing timeouts. That's what you need to know. And you can see that we simply run client.getProducts. So the same we have seen in the definition in protocol buffers, you can see it here. So you simply type getProducts and you receive a stream. Very similar to what you've seen in the protobuffer definition. We have a for loop where we consume the stream. As long as there are no problems, then we simply put them to internal array. And at the end, we print them in line 70. The compilation is trivial. And the output, you can see that we have received the products. But I mentioned that this is a polyglot approach. You don't have to know specifically Golang to use protocol buffers. So quickly, can we do this in Python? Because if you're not familiar with Golang, then maybe Python is good for you. Also, some couple of lines of installing gRPC, which is not very important. What's important is that we have produced two files, shop pb2 grpc.py and shop pb2.py. So basically, the code generated from protocol buffer is placed in those two files. And the client is as simple as those 10 lines, out of which 3 are just imports. So we import gRPC library and 2 files that are generated for us for free from our proto file. And then we open a channel, so basically connect to a socket. You can see that there is insecure channel in this invoke because basically gRPC will force you to use SSL, especially in production, so you have additional encryption in place because just for safety. Then when we have this channel, we simply instantiate a stub. As I mentioned, stub is roughly the same as a client, just terminology. So you have a stub and you want to use it. How do we use it? In Python, this is even cleaner than in Go because the products on the left-hand side will be a stream, and it is created by calling getProducts on client. You can see that there is this instance of product list requests on the right-hand side because we simply said in the protobuffer that there is an empty message required. And how do we consume the stream? Well, in Python, a stream can be consumed inside an array. So you can see that we simply print each and every product in a loop. And of course, this is the output of our Python client. So writing client code is as simple as it can be. Like only boilerplate from your programming language makes it as large as it has. Can we do it in other languages? I won't bother you with the implementations in every of those, but these are the languages that are supported by the authors of gRPC. If your favorite language is not on the list, don't worry, because there are community builds. For example, in my company, we use Scala, and for Scala, we were able to quickly find at least 2 implementations of gRPC based on specific frameworks underneath. So, yeah, this is kind of polyglot. And, yeah, we are going to the summary. So, what we have learned, we compared gRPC to REST. We could see the differences. I don't claim that one could replace another. Can't imagine like browsers talking to servers with gRPC, but I can imagine internal services that we build for our own companies. This protobuffer is more convincing, at least to me, in terms of defining what services are doing. We have gone through the implementation and the syntax of protobuffers. I know this is just like a very brief thing, and I don't want to go through the whole documentation. But there are specific benefits that only are present in gRPC, and the main benefit for me is protocol first. So you don't bother with technology as long as you don't have to. if you are talking to your product owner or someone business related, then you can talk about things that are written in protobuffer, and they will roughly understand what you're talking about. You have type safety, and there is like half of people like dynamic languages and the half do not. So for the second half, this is something beneficial because you don't have to verify the types on your own in statically typed language. This is a polyglot, so you can use whatever language you want. It's easy to bootstrap for each of those languages. I have shown you this was like 2, 3, 4 lines of bash to install and compile the protobuffer. And compared to, strictly speaking, about protocol buffers and JSON, you have smaller messages in terms of the thing that goes through the transportation protocol, and it is less CPU intensive. So if you're writing things that encourage mobile devices, maybe this is a serialization format for you. In case you have any questions, this is a good point. If you get to something new after this talk, you can also contact me. There are some contact information. Thank you.
Yeah, very big applause, please. This is the last chance to do that. Actually, thank you very much, Michał. Michał Pawlik, about the ins and outs of gRPC technology.